Thank you, Kathy, for joining us. I will give a brief introduction of Catherine Truffert here, and then she will start presenting a very exciting talk. So Kathy serves as the Iris Instruments as the CEO. If you don't know what RF instruments are, basically they are the manufacturer of a great variety of high quality geophysical instrument. I have been a customer. I'm very satisfied. So thank you, Kathy. She's been serving since March 2017, managing day-to-day operations, working in research and innovation with electrical engineers and geophysicists to kind of, electrical engineers might not know a lot about geophysics. So she's trying to move everybody in one channel and working on the same thing and tackling all the challenges and kind of answering the questions the customers have, as well as the stakeholders and the employees of the company. Kathy holds a PhD in geophysics from École Normale Supérieure in Paris from Marie Curie University. Hopefully I did not butcher the French pronunciation there. In France, she worked more than 20 years in the French Geological Survey, or BRGM. She developed a strong expertise in research, especially geophysics, geology, seismic gravity, airborne, and business development, including strategic and business plans, research and development programs, and as well as intellectual property, as well as management. She successively led the geology department and research division of the French Geological Survey before joining IRIS as a CEO. And currently, Catherine is the administrator of French National Research Agency, president of a CRESITT Technology Resources Center, and the president of Nantes Observatory of Sciences of the Universe. And she sits on a various big scientific committees, including Institute of Mines, Telecom, and so on. But maybe the most important thing for us as the Society of Exploration Geophysicists community is that she serves as the director at large on SEG. So without further ado, Kathy, thank you very much for joining, and please let us know about this exciting research you're doing.
And thank you very much, Sina. It was a long bio, I guess. So sorry, so just to bother you with that. So actually, it's me. So what I am, I'm a geophysicist who worked also in geology, and it's very, very important to do the link between so hydrogeology and geophysics. It's very important. So the first picture, so just I put on this slide, it's the Pont du Gard, which is just an aqueduct from the Romans. Just to have in mind that water, it's not a new topics. It's something that was in the minds of many humans, and so even centuries ago. I thank my co-author, Jean-Franco Morelli from GeoStudy Astier, and the examples I will show you so is coming from his team in Italy, and the final client was ACEA, which is actually a water company, so the water company, I should say, for Roma. And so they fully manage so the integrated water services in more than 100 communities, municipalities in the region of Romas. Okay, so go ahead. You will see. So the total volume of liquid fresh water so is not everywhere the same, so globally actually. And what is very important to have in mind that so everywhere in the planet we suffer or we will suffer from lack of water, so fresh water, I mean. And today, so in 2022, it was very difficult, and 1/3 of the population, so about 2.3 billion people, were under water stress. So it's very, very huge. And since to all 160 million of children suffer from water shortages due to severe and prolonged drought. And it's very important to see that the climate change doesn't help, actually. And this is one of the thing that we should, as a geophysicist and hydrogeophysicist, it's very important to continue to work on this topic, because we will need it so in the future. And so basically what we have to keep in mind is by 2050, so we will have many billion of people we will live so in a water deficient territory. And you do not have to say, okay, it's only developing country, or it's only from the south. We do, as Western country, we do suffer as well, even so today, from a lack of water. Even in France in 2022, we had to supply so some villages and communities so with a truck of water, and they didn't have, they were just lack of water. There was a water shortage. And what is important also to know, and it's very problematic for us as geophysicists, it's that the equivalent mean depth of water is different from place to place. So basically here, so on the left you have so the mean depth by main continent, but in one continent, basically you have a lot of difference. Okay, then the fresh withdrawal. So in 2017, you see the aggregate by continent here, and you see that the freshwater was the withdrawal was very important. So it increased about 3% per year. So in the period of the 1950 to 1980. So it's the picture on the right, the top right. And it was partly due to a higher population growth rate, and particularly to rapidly increasing groundwater development and irrigation. So you can see that specifically in India, for example, you can see that the need for the agriculture is so high, and even it didn't stop. So it's the increase is still here. Today, so the rate is about approximately 1%. So and it depends about so the current population growth. But basically, we will continue, okay, to need more and more to use more and more withdrawal, to use more and more groundwater. It's very important, and this is for agriculture, as I said, domestic use, but also the industry. And the industry, as well as the new industry, I should say, so all the IT industry, for example, is also use a lot of groundwater. So after that, yes, I just pointed out that India, it's very so a huge amount of water, so we use so for the for the agriculture basically. But so finally, the hydrogeologists, what they made, they tried to have an indicator. So they called it so the blue water scarcity indicator. This is a ratio between the blue water footprint and the blue water availability. Okay, and you see on the map, so so all the map with the countries, you see this indicator is very important, because you can see that as soon as you are above 1, so that means so more than yellow, orange, and red, you can see that it indicates the number of months per year in which blue water scarcity exceed 1, and so it indicates so an unsustainable rate of withdrawal. And you can look at some continents. So Europe, so it's for us, it's very clear. As soon as you are in Europe, you can see that in Europe, for example, so in Spain, Italy, it's very difficult. So for some months and many months during the year, so you are lack of water. So you have to manage that, okay? It's the same in France, for example. We do have regions so very different from place to place. And it's exactly the same for US as well. So it's very important to understand that, and to understand as well that it's getting worse. The next, I just wanted to show you, so this global hydrogeological map. Okay, this is global, so that means so you cannot use it so for your day-to-day work as a hydrogeology, but it shows you that there is discrepancy between the places, the continents, north, south, near the ocean or not. And you can see that you have places, you have some large aquifer that are able so to have a recharge and other that cannot. So for example, so the blue one, so the major groundwater basin, so it's sedimentary basin basically, it presents so in general the most favorable conditions so for groundwater withdrawal. That means in this region, so basically you don't know very specific hydrogeophysics, okay? For the green one, it's areas with a complex hydrogeological structure, and it contains so thick sequences of formation that also transmit significant quantities of groundwater. And the problem is that their productivity tends to be less than that of the major groundwater basin. And you need to have more tools in your hand, and basically hydrogeophysics. So geophysics is one of them. And the third one, this is the brown one. It's also this region, so are less favorable areas for groundwater development. And it's very important to see that even in those regions, so you need definitely hydrogeophysics in order to implement, to know where to drill, for example, to better understand the aquifer, to better understand where you will have the best flow rate, for example, where it's possible to recharge artificially or not, because it be also topic more and more in some countries. I don't talk about France because we are still, it's still forbidden to have an artificial recharge, but it's not the same everywhere in the planet. And I hope that this will be different so in the future, because otherwise we will be in trouble. Yeah, so this sketch, I pick it up so from the BRGM. So I love this kind of cartoon, I should say, but just to focus on different aquifers, and these different aquifers so need different geophysical approach. Okay, the simplest one, so when you have a good flow rate, there is no problematic, okay? You can be in deep sedimentary aquifer, so with chalk, with sandstone, there is no issue with that. But in others one, so for example, so we can pick up so the volcanic aquifer, you can have very low rate flow, or you can have large one, but it depends about the geology itself, and even about some parameters that can be depicted via the geophysics. It's why geophysics is very important. Fracturated rock aquifer are very difficult as well, and glacial deposit as well. So in this kind of aquifer, definitely geophysics is very important. And it's here we are. So what is hydrogeophysics? It's geophysics for hydrogeologists. And I know that because I tried to all my career to bridge the gap between the geophysicist and the geologist. And it's not very simple, okay? Because in geophysics, you want to have something not homogeneous, but okay, you don't want to have so much complexity actually. But for the geologists, they need to have a response, and for that they need to have parameters that for them it makes sense. And if you talk about with them, so and you can use words that and all the party they can have a wall between them. So it's very difficult to bridge the gap, okay, between these two main geology and geophysics. It's why for me hydrogeophysics is very, very important, because it's something that happened in the 90s, okay, and it dedicated for hydro. It's very important that we were able in hydrology, geology, and geophysics to bridge this gap. I think that I had to explain so very briefly what is induced polarization, because many people using electrical resistivity, they don't use induced polarization. It's a pity because you can do both with during the same times on the field. Okay, you will spend a little bit more time because you will inject current not only in the positive, okay, and then you have to come back to a time off during a period, and then to come again to a negative current because you change the polarity. But the thing that, yes, you need the time off in order to register, so the chargeability. So the induced polarization, this is a method that help you to have what we call the chargeability of the reactor. What does it mean? It consists of an injection with AB. So on the left, you have 80 electrodes. These are the injection electrodes, okay? You inject a current and then you get a voltage with two other or many others electrodes now, and you get voltages via M and N. And here, so for the induced polarization, it measures the capacity to hold an electric charge over time by injecting direct current to the ground, and then abruptly you turn off, okay, the current. And the induced voltage will decay over time. The higher IP, the longer over time, so charge is held. IP decays over time is few seconds, okay? And as a result, in addition to the resistive measurement, so capacitive properties of the subsurface material can be determined. Is very important, and this is during the same field survey. So probably many of you so continue to use it, but I don't know exactly, but it was the purpose of my talk. So it's why I wanted to just explain that. And okay, but basically, oh, sometimes it's a lag to change. Okay. So, but what are the main factors of the induced polarization? These are the mineralogical composition, the texture, the moisture, the chemical composition of interstitial water, the electrolyte, and so you can have also information regarding pollutants. But here, what we want to see for in this topic, it's the membrane polarization. Why? It's because it's a way to decipher where you do have phyllosilicates, so that means clays. And these so bring some phenomenon very specific. And what are there? So this is so membrane polarization or electrolytic polarization, whatever. But it occurs when there are fibrous lamellar minerals in the soil, and which have negatively charged surface particles that attract cations present in the electrolytic solution. And then these tabular clay particles are minerals in which this situation is best realized. Okay, so phyllosilicate are the main mineral that's for which it happens. And then what you have, it's a sort of obstruction, a clogging, and then you have that means when the current is sent to AB electrode, so you have the passage of the ion so is obstructed, and positive ion pass through the cathodic clouds, and then that means so you have a zone of ion concentrated form, and it's the different mobility of ion that determine polarization. And when the external current ceases, when you stop your so with the time of the ion clouds that are neutralized by diffusion and maintaining a transient, so a secondary current of the same sign as that apply. And it's exactly what you are registering, okay? What you are registering. And it's very specific to clay. I won't talk about the electrode, so polarization, sorry for that, because it's more so dedicated for the mineral exploration, and it's not our purpose. Okay, I won't also talk about, so here I only talk about the time domain, okay? But there is a spectral induced polarization. So it works, and that means so it's higher frequency. And so here you don't see the decay curve, but you look at the different behavior with different frequency of the excitement. And but again, this is a very high field of still in research. I think it's promising actually, but so so today we only focus on TD IP because we think that today it's the way to do a survey in a time period which is okay to be on the field. Okay, otherwise you have to spend more time. again, perhaps in the future, we only will speak about SIP, but it's not the case today. So come back to our aquifer. So for distinguishing so area rich in clay, so the phyllosilicates, what we need to track the low permeability, and that means so you need to track if you want to avoid places where the clay are. That means very low permeability, and it's very not good for hydrogeologists. That means you need to avoid any anomaly with chargeability. It's why during your survey, if you can, really do ERT, electrical resistivity tomography, but also chargeability in order to decipher if you have some clay, okay, behavior, if you have chargeability, and then avoid this type of places in the model of the anomaly. So it's in many aquifer I talked about before, so the glacial deposit, but also the fractured rock aquifers, the weathering zone as well, because you have clays and shale due to the alteration of the crystalline rocks, but you also do have very high porosity rocks. Can be a very good aquifer when you have fractured granites, for example, and something else. So the thing is that in the same place, you can have all these kind of features. So it's very for you important before drilling to know where to drill and to be sure that you will have a flow rate enough in order to retrieve the water you need. Then we can come to the example. So GeoStudy Astier brought to me. It's very interesting because as many big cities, Roma so need water. Okay, and the thing is now they are looking for not very close to the city because of the pollutants also first, and because the activity, and so it's better to try to find groundwater, but a little bit far away from the city. And here we are about 40 kilometers far away, and the site, the area to be so just studied, it's a very large one, so 95 hectares. And the other thing is that it's also difficult. So you will see, but it's really hilly and a dense vegetation area, a very rough terrain. And so they could have done standard, I should say, 2D or even 3D line, but with resistimeter, traditional one, with cable. It works well, but the thing is that the terrain was so difficult that they can also work with such traditional system. So you see, this is really a typical village in the Inner Apennine chain. So in Italy, you see it as a very small village, and you see that it's hilly as well. And so the name of this village is Persile, and it's at 575 meters, so in altitude. It's a regional natural park as well, so it was also difficult. They cannot do whatever they want also in terms of geophysics. And so you have the range of the elevation is about can go up to 1,000 meters. Here is the geological map from the 50,000 scale, but they did also some geology investigation plus the geophysics. It was very important for them in order to be able to decipher where were the calcareous limestone and the calcarenite. So this is the SPT1. So you can see on the center actually, and the moors and clay. Very important for our study, and the limestone, but also with more alteration. So you can see that it's not so easy for hydrologists because this is not really classical, I should say, aquifer. It's not standard sedimentary aquifer. You can see that you have very main features. So you are in the subduction zone, so of the Adriatic plate, so coming beneath the European plate. You have outcrops, so from tertiary to quaternary, and the quaternary is post-orogenic. And you can decipher some north-northwest trending complex plicative, but also fault geometry of a trust as well. And these are also displaced by perpendicular post-orogenetic, so east-west faults, normal faults and transcurrent faults. So really the geology, as you can see, in terms of lithology and also in terms of dynamic, geodynamic, is complicated, very much complicated. And back to the zone of investigation. So also the altitude is a little bit tricky. You can see here with north east west. I think it's not a north south. So just cross section with the altitude. You can see that yes, you can just lose 200 meters in a few hundred meters. And so what they decided to do is to use, and I will explain that to you, non-conventional. They were not able to use resistivimeter, classical, I should say, with a multicore cable. It was not possible because of this hilly terrains, and again, with a dense vegetation, it's natural park. They were not able to cut trees, for example, and the large area as well, because they had idea where to put the drilling, but it was really far away from one to the other. So, and another thing, it's that they needed to do it in a few days. So they use IRIS instrument system. So it's what we call the full waver. So basically, it's nodal receivers, two channel receivers, and this is this box here in black. And you see that there is no cable, okay, in between each boxes. This receiver for two channel. It's the sampling rate is 100 hertz, and everything is time stamped via the pulse per second from the GPS. They put because so for that they made a simulation in order to know exactly more or less where they could put so the full waver, but also the length of the dipole, and they decided to have a length of 15 meters. So 15, you have three electrodes and two dipole per boxes, and boxes. So the dipole is 15 meters. And so this is for the receivers. And you have also another receiver, but it collected so the current, okay, the current, so recording at the sampling rate, and it's linked with the transmitter, and the transmitter is itself powered by a motor generator. So satellite connection is very important for everything, but you see there is no cable in between the boxes, which is very important for this kind of survey. Here also for search campaign, it's very important to position in really an adequate mode, so high positioning system, in order to get all so the location of all the electrodes, receiving electrodes, but also the current electrodes. So I didn't talk about that earlier. I can come back to the block diagram. You can see that with the orange dots here, these are the injection points. So for one moving electrode, for example, basically what you can do, you can have one fixed electrode and then have one moving electrodes, and then you have dipole of injection. You can do whatever you want, okay? It's really flexible. You do have to be very cautious, okay, with the managing of the transmitter, and for all the team on the field, it's very important to know when you do inject. It's basically, it's really in terms of safety is very, very important for that. So different from the resistivimeter, which is it makes it by itself, okay? So when the resistivimeter runs, you do not just touch any electrodes and it's okay. But here, okay, basically it's very more not difficult, but you need skilled people very rigorous to say, okay, here now you don't touch any electrode, I do injection. So back to the digital elevation model terrain. So you can see here the red dots where all the injection points the team made. So here again in the red dots, these are the transmitting dots, the transmitting position of the electrodes. And in yellow, because they wanted, so the team wanted to go fast, they didn't want to spend time to know where to put exactly, so the full waver and the electrode. They decided to do the dipole not in a more or less perpendicular mode, but they put it in the same line. And because you have seen that north-northwest trends was in majority so the overthrust and things like that, and but they were thinking about so also the east-west so faults that were post-orogenic faults. They used all the track and roads in order to put so the electrode, 3 electrodes by full waver, the receivers. Okay, and for the transmitting, they also used so the track and the roads, and along with, so they did a lot, probably about 60 transmission. And so you see that they went far away, and they have, so from side to side, they have about so 900 meters. So what do we collect for one channel of one receiver box? Here it's the red. Here it's the time. Okay, you have the time in horizontal, and here this is the value of the voltage. In blue, this is the value of the current injected. So you recorded with the box I told you about is linked with the transmitter. Here, the green, these are the time per second, so the PPS, okay? So during the injection, you do have so timestamp, so the current, and here one channel of potential. This is during the injection, but you inject not all the time. So that means you also have many recording without any injection. That means it's a spontaneous potential, okay? In your data, you don't have only the data with an active mode, but you do have also during a passive mode. What did they select? They selected to have 35 stacks. So they wanted to stack a lot in order to increase the ratio, the signal to noise ratio, because again, they were very frightened to do not just select an area where they could have so clay and other stuff like that, and they wanted to have a high porosity and high permeability as well. They spent 3 days on the field, even if they spent a little bit more before in order to do the GPS positioning. But they spent 3 days, 12 people, 1 day to carry on the 30 boxes. So they have 30 boxes for the recording. So that means 3 electrodes per boxes as well. So they put everything on the field. And then after that, you do have 1 day of injection. So the injection, as you see here in blue, this is a 2-second so AB, and then 2-second time off, and then 2-second you reverse the polarity, and 2-second AB plus, etc., etc. And so that means they did that so during 2 minutes in order to have 35 stacks. Okay, yes, so they did, as I told you, so more than 60 so injection, and so that means so they collected a lot of data, and these are the data. This is the point clouds of measured apparent resistivity here in the red dots are the injection points, and here all the clouds, so underground, so the clouds of the data where it has been lighted and where they did have information. So that in total, they did have 3,068,618 measurements, and they reject about 1.3%. So regarding mainly rejecting, so the apparent chargeability less than 0.05 millivolts, and also some outliers apparent resistivity. And after that, they made so an inversion, so resistivity inversion, and then after that, they also we do some removal for IP, because again, so it's much more noisy for the IP and the chargeability. And then so they removed all the IP value with standard deviation up to the more than 40%. That means again, so they just reject about 35%, and so they retained 65% of data, which is really enough to do the inversion. So for the inversion, you can see this is a mesh of 12.5 meter, okay, and the depth of the investigation went through 425 meter. And the started model for the resistivity inversion is with 80 ohm meter, which is the average of apparent resistivity. And the starting model for the chargeability is about 3 millivolt by volts. So the estimated noise, so for the resistivity is about 1%, but for IP data, it's about 5%. So you see, even if they're rejecting more data, they still have a little bit, so higher, I should say, noise, so in the chargeability. And we can see that so really on the map, but actually this is really, really good data. So here, this is the ISO depth from the surface, 100 meters. This on the left is the resistivity map and the chargeability on the right. What you can see again, so I just draw here in white, so the main first features and also large plicative, but you can see that here, if we remember, so the geology map, but I will show you again. What we can see here, this difference between so very low resistivity, so high conductivity, and here high resistivity. These two blocks, these are controlled by the lithology itself. So two main difference, so in the lithology, so bring it this obviously, and it's the lithology itself controlled by the faults, okay? And here for the chargeability, it's less obvious because it looks more noisy for 100 meters, but when you go a little bit deep at 150 meter, you can see, so here, so the frequency is lower, and you see that it's more easier to see here that you have very, very low chargeability, so almost zero in this formation zone. And here you still have higher chargeability at the depth of 150 meter from the surface. Okay, this is an ISO depth. Okay, so that means so it's the surface just follow the topography. Here it's different. This is the ISO elevation. That means it's 425 meter. Okay, so above the sea level. And then you can see again the well-controlled anomaly controlled by so the features, so the tectonics, and also as well the lithology between the block in the western part and these two blocks. Why I put 1, 2, 3? It's because beginning so. Early in the story, so they selected a free zone where they could put some the drilling, because for drilling like that, you have to be close to the village, and so Persil is just here. You have to select a place. You cannot drill everywhere. So that means they needed to be sure. So they selected places, and then they wanted to know, okay, where it's possible or not. And you see here for the chargeability, so here it's really more, I should say, evident that there is two different of behavior in terms of chargeability, with very low chargeability, so in the western part, and higher, so in the eastern part. Here, this is exactly the same map, iso elevation map, and these are east-west so cross section for the resistivity, and below this is the chargeability. And you can see again, so the position, they didn't know exactly at which depth they can so put the drill, but just to have a look of okay, the verticality, so what they could have. So again, it's a model, okay? An inversion is a model. I should have so started with that, okay? It's a model of what we expect to have, but it's really interesting to see that here you have really a high conductivity zone. If you are a low conductivity zone, okay, it's more tricky because we are very close to the main fold and the main structural features, okay. And here, so for the chargeability, it's also not so obvious, but what you can see, it's for both of them. So in this region, for the high conductivity and for the region of high resistivity, both of them are more difficult so to interpret it in terms of chargeability. So they went to another cross section very close to the zone 1 and 3 that has been decided, and they were more confident to have, so okay, the third the zone number 3 with a high conductivity, that mean okay, that mean we could have a place where we can have fresh water. It's possible. Here it's okay, probably the porosity is good, but the thing is that probably they are not in the zone where there is a saturation of water. That means sometimes you can have water and sometimes you cannot have water, even if you do have the good geology, and basically probably it's limestone. You have for both of them very low chargeability, which is good, okay? That means you do not have large amounts of clay that could be difficult for you in terms of rate flow. And so here, the depth of investigation finally is about 400 meters. And it's where they will drill. So basically, and they expect perhaps in a lower position, but they expect it to be. And you can see, so finally, when they look at that, say, okay, the zone 2. The problematic of the zone 2 is that we are very close to this accident, even if it could be very interesting, could be. But the thing is that there is no cylindricity in the geology, and it's very difficult to know exactly where we will be during the drilling. Again, this is a model, even if we are able to here to interpret in terms of geology. So here you do have different the features here, the limestone, and also very high conductivity at the near surface. Here a lower, much lower, so high resistivity more, and again low resistivity and high conductivity. You can relate it to the 3 main formation they did so see on the field with the outcrops. It's still really difficult to position something along the fault to be sure that they will have a rate flow enough. So, and again, they were tracking high conductivity in order to be sure to be in the zone, so in the saturated zone. So that means they removed the abandon, so the position 2, because again, it was really too close to the fault. And they were thinking about the position 1 and the 3, but finally, for sure, they decided to go directly to the position 3 because it's where so did have conductivity. And here, the chargeability helped them in order to know where exactly to drill and how deep they did expect to just cross the geology, able so to avoid any moss and clay, because this is, as geology, this is the limestone mole alternation. And so they have to be very careful to stay in the limestone and to do not just be only tracking in the moles. That even the moles is good to have a reservoir, but it's not good to just retrieve the water. So finally, they selected for drilling the third zone, definitely. And they were also happy to decide to do the IP as well, and not only the resistivity, because it helped them. So not only to position, because only with resistivity they could have selected the position tree, but what was very important for them also, it was to know exactly how deep they did have to drill. And it was also important to know that in advance. And so in conclusion, so this deep DC electrical survey finally used unconventional geometry. They could do whatever they want. Because they have to just adapt themselves to the field, and this is a really difficult field. And also, when you have such thing, the thing is to simulate in advance. So if you can do a matrix of sensitivity, is really the best you can do. In order to know what could be the length, for example, of the dipole unit, it's very important to do that. So again, that means that you have to be a little bit more skilled. So people dealing with that means they have to work on that, okay? It's not so much complicated, but you cannot just, okay, I don't know anything about geophysics, but I can bring my resistivimeter, I can do whatever. I take data, and after that I will have some support, okay? You have to be sure what you do before going on the field. Be sure that you will do that, but they adapt. What is very interesting in this example is they did adapt themselves, but they adapt themselves to the field actually. It's why, again, so why they put so the electrodes, so of the full waver, the receivers, along the line, along the track, along the road, okay? Because they didn't want to spend time to just find the real place where it's possible to put two perpendicular dipole of 15 meters. The survey design was really guided by site constraints, and the resistivity and chargeability data finally. So again, it's really simultaneous. That means so you do have two parameters, very important parameter during the same time. And the interpretation also together with geologists is very, very important, okay? Otherwise, you can missing. And again, you do have a 3D block after inversion of the chargeability of the resistivity or conductivity, for sure. But these are model, okay? These are model according to the inversion, okay? So you have to work all the time. You have to work with hydrogeologists or even geologists. So this the combined interpretation of IP and ERT so made possible to select the drilling position in this example, which was great. And yes, for sure, as a provider, so for as an instrument like that, I'm very happy to see that. So, and I'm proud of Iris team as well. And I hope you did enjoy so the presentation. Okay, and so I'm waiting for your questions, and thank you for your attention.
Thank you very much, Kathy, for the very nice showcase of the IP being beneficial for hydrogeophysics. Recently, my student actually published in the leading edge exactly about the same thing of using IP to kind of navigate through a very clay environment for finding the best position to drill a well for one of the farmers here in Oklahoma. So I'm going to jump to the questions quickly. Richard is asking, is it necessary to use non-polarizing electrodes to conduct a joint ERT and IP survey?
We do have customer who never use that, okay? I think that this kind of question could be asked to our customer again. I know that in many cases, they use, yes, pot, but we still have people using only iron stick. So it's possible. It depends about, I guess it's really depend about the geology. Okay, it depends about the contact resistance you can expect on the field. It's not depending about I want to do IP, so I need to. I'm obliged to do that. Okay, sometimes even for ERT. It's much better to have copper pot, okay? And so it's really depend about the contact resistance that you can expect.
The next question is for me. I have recently purchased this same equipment, and I was wondering, is it possible to just have one dipole current injection, let's say, putting it in place for monitoring this device and just have everything in place and do continuous monitoring over time? Do you still get a 3D image of the subsurface? Or you have to move this injection to get better resolution?
Actually, you do have two things. If you during the injection time, you do have what I saw the IP. Otherwise, it's spontaneous potential. But what do you want? You want to do to let a dipole of injection. But when will you inject? You will inject. So you mean just fix. You want to put a fix and sometime to record one fix.
Yeah, exactly. So just basically everything is in place. Let's say we want to track the contamination plume movement in the subsurface, okay?
Yeah.
And then over a long period of time. So we put everything in place and just keep recording. We will still be.
For sure, there is no constraint for that. You can do that. It's again. So what is good with this kind of thing is that it's very flexible. Okay, and it's your idea. It's your innovation. Okay, this is an equipment. Okay, and only an equipment, should say. Okay, you can do whatever you want with. But the thing is, more and more, I think that we should think about the monitoring. And exactly what you talk about, and for that, it's yes, for sure. If you let the dipole exactly the AB, okay, AB injection dipole at the same place, so that means if nothing happened, basically underground, if nothing happened, you should have exactly the same ERT and IP response basically, okay, but many things happen. And it's probably what we want to understand exactly. It's what is happening underground. So yes, probably it could be a good way to do. And you can also just do this, but you can do it when you are on the field, and you can also do active with other dipole, and time to time just record with exactly the same dipole. You see what I mean? And then all the collation of your data, you will have a traditional standard survey, and then you will have something a sort of monitoring with exactly the same dipole. I think it could be a very, very good way to understand if we can decipher what happened underground.
I got it. Awesome. Next question is from Sud here. They're asking any lithological limitations for this IP survey, or can IP survey be used in any rock type or groundwater exploration?
No, I think any type. So after that, for sure, you all the time have limitation. For example, the depth of penetration, depending about the geology. Okay, if you are in a very highly conductive surface zone, okay, that means you need more power, you need larger dipole. But the thing is that because you have the flexibility to do whatever you want, you can adapt yourself on this kind, not only on the geography, on the rough area, but also on the rocks itself. And so there is no constraints like that, but again, you have to adapt, and you have a large panel about the power of the transmitter, okay, the length of the dipole, AB dipole, so you can do small, during the same survey, you can do small one and large one, okay, in order to go deep and to have a higher resolution close to the surface. You can make things like that. After that, so the limitation is also the inversion code, depending about what you use. And because you do remember that all the inversion is made in 3D.
Okay, yeah, I think that's actually one of the other questions we have. But so the next question again is for me. Sorry. So I'm curious why the the aquifer zone was so conductive, isn't like fresh water supposed to be resistive?
It's because it was the non-saturated zone. It's the limestone where, and it's why. So finally, they didn't just find this. So they wanted to have something. Yeah, it's so normally you do not have a standard thing, but you need to find something conductive. Okay, the fresh water is conductive as well. But if you have to think about, so what is the non-saturated for the same geology, non-saturated zone with saturated zone with fresh water, because here they didn't have salty water. For sure, if you can have salty water because you are the forefront, this is also another topic. Okay, you will increase the IP as well. It will be more difficult to decipher with the chargeability.
Gotcha.
So it's again, it's because they work with the geologist. It's why they were able to, okay, this is the best zone regarding what we know. It's the best zone where we want to go.
You got it. Yeah, no, makes sense. Yeah, saturated versus unsaturated. The next question is from Jorge asking, is the IP inversion more or less uncertain, non-unique compared to ERT inversion?
So here, I didn't say that, but they use ERT Labs software, and this is really stable for 3D so inversion. For sure, inversion, this is a model. You do have a model, okay? You have parameter that help you so to just converge toward so the more realistic, the more, okay, which respond to the data, okay? But yes, you cannot have one thing and completely another one, okay? Cannot be completely different. But
Yeah.
for sure, you cannot say, okay, I do have a model. This is the reality, okay? But in geophysics, basically, we know that all the time, okay? You can do gravity, you can do seismic, you can do whatever all the time. You know that, yes, you need to know that as soon as you have to invert, to migrate, okay, to do things like that, this kind of post-processing, that means you will have a model, okay? But again, it's why I didn't insist on that. But for sure, depend about so the inverter, so the 3D software you use. There is some today. So you did so some other webinar on that. So there is many possibility. And again, I think it's in your hands. You can so try to work on that, and perhaps there is not one solution, meaning only one software.
Correct. That is correct. The next question is from Edwin asking, what kind of survey setup did you, array configuration you use, like dipole, winner, or you didn't use any of those?
Any. I think I don't know exactly what they did, but I know that many customer now, so they do not work with only one configuration pole dipole. We do when people they want to go deep, we recommend to do pole dipole. That means one remote electrode far away and then the other one, and then okay, so that means you have large dipole, okay. But if people they need to have high resolutions close to the surface, that means you also need so small dipole, okay? So in that way, you can deal with so other dipoles. So, but it's really so with the transmitter. So again, you have to be very cautious, but to do have also the possibility to have a shorter dipole inside the zone of interest, okay? But you can do that. You have to think about that before doing your survey and before even so knowing where you will put your receivers and where you will put your transmitter. But yes, you can do whatever. You are not obliged to do as we are obliged to do with a resistimeter. You can do whatever you want.
Gotcha. The next question is, can you share the presentation? We actually share the recording on our Slack channel. So please, if you're not part of the Slack, join by emailing ns@scg.org, and then you can have access to the recording of the meeting. The next, kind of question is that from James saying that shared wave velocity model generated through use of passive seismic method could use to be as an additional constraint to the subsurface model. Just a thought. And yeah, so for
Yeah, we
better
did
understanding.
actually what we did. Iris instrument was involved so within a project, a research project. Okay, sometimes we do that in order for us because we develop equipment, but we want to know what we can do with it. Okay, and then we were in a volcano in the West Indies, and we worked simultaneously with the full reverse system. Okay, and with a nodal passive seismometer, 3 components. And it will be published so in 2024. But so it's very, yes, for sure. That means because it's the same philosophy. Okay, it's nodal receivers. Okay, you can use it passively, and we did also a passive register in order to monitor the volcano. Actually, it was very, very impressive. But yes, for sure, you can try to merge after that. It's really tricky to do joint inversion for sure, but you can try to interpret, because yes, the seismic give you information of the structural behavior of the underground. It's very important. So you do have access to parameters that are very important in order to understand. So, and everything is complementary.
Thank you. So we have several questions in the chat box, but we're out of time. Please, for those who put their questions there, I would suggest that put your questions in our Slack group, and then Kathy will answer those for you, because we're at the 2 minutes past the limit of the time that we have, 3 minutes actually. So with that, I would like to thank you, Kathy, for giving us the opportunity to look at your research. It was a fantastic talk, and I really liked it. Thank you very much.
Thank you to everybody, and do not hesitate to send me a message. Okay, so I will like to respond, and even with my co-authors.
Awesome. Thank you very much. All right.
Thank
Have
you.
a good day.
Have
Goodbye.
a good day. Goodbye.